All right. Good morning, everyone. Welcome to our final day of the sixth workshop on EO and AI integration for agricultural statistics. It's been a really enriching week, and we are happy to have all of you with us today with the wrap up and topics today. We will dive into fundamentals of satellite images, time series, and explore the use of self-organizing maps to enhance the data quality in agricultural statistics. Those are very powerful tools to manage and interpret EO data, especially when work with large volumes and noisy field observations. Uh, I, we are thrilled to be joined today uh, with our speakers, Mr. Gilberto Câmara from FAO Brazil, who brings his expertise in seats and geospatial infrastructure. Stefania Pizarro from INI Chile, who will share a practical case study from her institution. And once again, Lorenzo Simon from FAO, who has been with us through all the workshop, guiding the sessions and discussion. Please join me in giving a very warm welcome to everyone. And I will pass the floor to Lorenzo. Lorenzo, the floor is yours, okay?
Good morning, colleagues, and good afternoon. We are here on the third live event with our distinguished speakers. I will just introduce the topic, which is the relevance of in situ data for training machine learning algorithms and their relevance for field surveys and the link we need to make sure that this data is then useful for integration with Earth observation data. So I'd like just to share my screen because I just have 3 slides. Okay. Let me share the screen. Okay. So as we know, algorithms need this data. Now, where can this data come from is an important question because of the sustainability. Of course, one solution could be that the data collected by NSOs could become the main source of machine learning pipelines. So they could feed training data to algorithms, which can be then in turn retrained and become more and more specific and accurate. However, we know that while national surveys often adopt GPS technology, still NSOs are really lacking to use largely remote sensing data. So we had in the past an effort made by the Global Strategy to improve agricultural and rural statistics, and there was a compilation in a handbook of remote sensing for agricultural statistics, 2021, if I'm not wrong. And it was highlighting the missing links between Earth observation-driven survey and most common NSO surveys. I encourage you to refer to this publication, which is very interesting. And then as of practice, as of projects, an Earth observation more related with quality assurance of the in situ data set has been developed in collaboration between the FAO EOSTAT project and the European Space Agency Send4Stat project, which is really focusing at 2 main components: the evaluation of a survey design and the in situ data assessment using Earth observation data. So we have 2 criteria for the evaluation of the survey design. The first criteria is related really to the sampling design. So the observation timing should allow the identification of the crop type in the field, unlike some household survey where the survey must take place when the crop is visible in the field. Minimum number of samples for marginal crops, including intercrop types, to provide balanced data set in terms of crop type sample distribution. And as we see, sometimes this is not the case. We have majority crops are basically oversampled and minority crops, we just have few samples. That's a problem for Earth observation. And finally, local homogeneity of each sample unit to match the corresponding satellite observation footprint. Translating in other words, data should be also be stratified in the sampling design to reflect the different agroecological zones where the crop is cultivated. The second aspect related, of course, to the sample design is the response design. So georeference ground observation at field or point level, so we can link the satellite geospatial data set. Household geographic coordinates being insufficient. As we know, the household might be far away from the crops, maybe actually even very far away. And furthermore, one household can have different fields, different crops. Sample unit size, at least matching the considered satellite observation footprint, not only the spatial resolution. We usually suggest to consider at least 3 × 3 pixels or 5 × 5 as the sampling unit. Contextual observation to document sample quality and qualify its representativity. Rich labeling of each sample beyond crop type to indicate specific growing conditions, weed abundance, limited crop cover, water lodging, tree density, and high precision of crop nomenclature, including information about infrastructure and agricultural practices. Is it irrigated? Is it a greenhouse? Crop under canopy, agroforestry, species dominance for intercropping, which then answers to the many questions we received on how do we manage mixed cropping. Well, we manage this by having a rich label that informs us that in that sampling unit, we have 30% of this crop, crop 1, and 20% of crop B. Okay, and now we move to the, and now we move to the second part of this quality framework for in situ data, which is really the assessment based on Earth observation to control the quality of an in situ data set from the satellite remote sensing point of view. And this leads to the presentation that today Gilberto and Estefania have prepared for you. So we have several criteria. First one, completeness of sample information, including rich labels linked with geospatial features and survey data. Topology integrity of georeference features collected on the ground. So if we have polygons, they should not be overlapping, for instance, or they should not have a road crossing them. Metadata completeness, including geographic coordinates, system definition, protocol of geodata collection, typology definition of all crop labels and related attributes. Geospatial feature GPS coordinates accuracy visually checked using most synchronous Earth observation imagery. I presented a slide on the first day where we had those polygons that were mismatched compared to the Google base map. Sample purity based on multispectral reflectance heterogeneity assessment, so inspecting the signature of specific samples and understanding if that is really, the expected signature of that crop, or maybe we have a contamination because our location is not located appropriately inside the field. And finally, the labeling quality based on NDVI time series clustering and profile similarity analysis, which is going to be the topic of today's presentation. I just want to stress that this last topic, we're really talking about machine learning and artificial intelligence, which basically automatize processes which could not be performed manually because we're talking about thousands of data. So I think this is a big advancement for remote sensing, and I would like to give now the floor to the next presenter. I think it's Gilberto. Thank you very much. Gilberto.
Trying to locate Gilberto, but I think he lost the connection. In this case, can we go ahead with Stefania? Is Stefania ready?
Yes, I'm ready, but maybe I need the context. Good morning. Sorry. Maybe I need the context of Gilberto's presentation for my speech.
I can try to text him. I can try to text him right.
In any case,
Right.
I can present now.
Okay, let's see if we can find Gilberto. Just a minute.
Welcome, Gilberto. Let me pass the word to Gilberto so we can keep the presentations. Okay.
Okay. I deeply apologize by being late. I was actually caught up in rating. Just feel that 10 o'clock I had to be in. So, I mean, in connection with the workshop. Okay. So let me share the screen. And the screen. And hopefully this will come out. So I'll try to be brief and focus on the key points that I think are important for the testing. And I will cover some of those that you may be familiar and some of those that you may be not. And I think this is a diverse audience, so we might, apologies for those who've seen this, some parts of it, and I hope at least some parts of it will be new for everyone. So the whole topic that we're discussing is what we call Earth's observation analysis in the age of big data. And of course, as been highlighted, there are a number of satellites around, and many of those who are open in terms of their data, so we can use them for our work. And the question becomes, of course, the idea that the model that we are looking for is not a model where the agencies will host all the data. You may want to host all the data, you're an NSO, much as you do with agricultural statistical census for reasons of privacy. But in a world that the data is open, in some of the countries may not be worth it having a dedicated service just to host images which are accessible somewhere, which is similar to what people use when they use WeChat or Waze or some of these applications. Well, so in general, the deal here is we know what we want, but we need to know how to get there. We know that we have big satellite data around. We know that this data can be, in many cases, is already available somewhere on cloud services, but we want to put it to our gains by using machine learning algorithms. And the goal of it all is, in the end, what we call reproducible, reused, shared knowledge. The promise of open data will not be realized unless the data is followed with open software, which allows really users to be empowered and to use whatever they want and do not have to be constrained by commercial decisions. So I'm going to jump a little bit on this, and I will start with the Brazil Data Cube. As you know, there are many. I'm going to start from Brazil Data Cube because we are in Brazil, but this is one example of a system, a system which provides data for a country-based. Brazil is, of course, large enough to be able to do this and have resources. This is not a recipe that I would recommend for most countries, but Brazil has organized a data cube of Sentinel, Landsat, and CIBA's data, and that you can download your data directly from the repository. Of course, there are other resources available, such as Microsoft Planetary Computer, Amazon Web Services, Copernicus Digital Data Space Environment, Digital Earth Africa, Digital Earth Australia. And my idea, my suggestion is whenever you can use those services, do so. Don't build your own cloud service if the data that you want is available openly. So what is in common with all of these efforts? What is in common with all of these efforts is the idea that what you actually get from a provider such as Copernicus, such as Digital Earth Africa, such as Microsoft Planetary Computing, is a collection of the images that we call ARD, which is a jargon for analysis-ready data. Analysis-ready data is a data that has been produced by the space agency with conversion from raw data to radiance, and then from the radiance at the top of the atmosphere, you make the atmospheric corrections, and then you do a conversion to surface reflectance, and then produce the best possible product that you can for each image, regardless if, for example, there are many clouds here, the images particularly don't match, there are in the same satellite 10-meter bands and 20-meter bands in the case of Sentinels, for example. So by itself, a collection of analysis-ready data images is not fit for analysis. So you need an extra step, which can be done by the provider, but mostly it is done by software that you run on your own machine, which is conversion these analysis-ready data into multidimensional data cubes. So, for example, Digital Earth Africa does not provide data cubes per se. They provide analysis-ready data from which you can build data cubes. And the data cube is organized as a cube, logical cube, not necessarily physical, where you have dimensions latitude, longitude, and time. And this is how you produce, so I'm not going into detail. Copernicus, I'm going to jump a little bit just that we get to the main concepts here. So the analysis-ready data is like this. Image collections are not regular in space and time. Bands may have different resolutions. Temporal intervals may be irregular. So all of these is organized in such a way that it's the best that the space agency can do, but it's not what we need. So we need to put this nicely into a data cube. So when you take a data cube, you take what comes out of Microsoft, what comes out of CDSC, what comes out of Amazon, and then you say, okay, I'm going to guarantee that the temporal intervals are the same. I'm going to guarantee that they all share the same areas. Okay, you can be 1, 2, 3, or 100 MGRS tiles in case of Sentinel. They all share the same resolution. So then, as a result, you have two important properties of a data cube. Given one location, one pixel of a data cube, I get a time series of values equally spaced and belonging to pixels with the same resolution. And this time series can be multidimensional, can be NDVI, EVI, band 5, band 6, whatever. And all of these must be georeferenced to the same location on Earth, and the times are perfectly known. Now, if I cut in time, I'm cutting by latitude, longitude. If I cut in time, I have one image, one band or multiple bands for a certain temporal location. And the selection of the area and the selection of the temporal interval is a user decision. It's not something that the data collection provider can do. For each kind of application and for each kind of Institute of Data, there are the most, let's say, different compromises. So, for example, for a Sentinel-2, where you have 2 satellites in a tropical area with significant cloud coverage, people use normally 15 days. For a Landsat 8 image, where the images are good, the quality of the images is very good, they pass every 16 days. Normally, people take 1 month or 2 months. And for Landsat 5, which is already have some problem, it's an old satellite, maybe 3 months is a better bet for the temporal resolution. So there's no rule that you can ask. You have to know yourself. Okay, so again, I'm thinking about not necessarily how to build a data provider repository for, like Microsoft has done, or Digital Earth Africa has done, or Copernicus has done, or Brazil Data Cube has done. I think this is for professionals that know how to handle big images. Now, you sit here in the middle and you say, okay, I want to get them. I want to get an image from Microsoft or from the Copernicus, and I want to do this with as little effort as possible. And this is done by a protocol which is called a STAC, Spatial Temporal Asset Catalog. This protocol ensures that you can query the contents of the provider, and if the data exists, it will allow you to access the data on the provider. You can implement this at a higher level, lower level. The principle is the same. You query the data set and say, do you have the Landsat image for data so-and-so and for place so-and-so? And the provider says, yes, I have it. No, I don't have it. Oh, yes, I have it. Here's the link to download these data sets. So this has revolutionized completely the world of big data, big Earth observation data, by providing a standard way to interface to the big cloud providers. And of course, is the main reason why you don't need to be your own provider. We have, and I will not go in too much detail, probably you've heard, that the team that's led by INPI has developed a package called SITS, which stands for Satellite Image Time Series, to access the data cube. It's not the only package available. There's another package called the Open Data Cube, done by Digital Geoscience Australia. They all come similar, a little bit different. One is in Python, the other one is in R. But the point being is that they aim for you to be independent of the data provider. So, in terms of agriculture, what are we gaining by using data cubes? What we are gaining is the ability to represent the temporal evolution of the features in the ground, which hopefully represent the temporal evolution of the crops and the agricultural products themselves. Of course, it's not a one-to-one situation, but it's close enough that it provides you with information that we call a time series of a pixel, which, for example, in different times of the year, will have different responses related, for example, to the changes that have taken place in land. So one obvious thing is to separate, and this is a tough one to do if you're doing in a single image. Very tough to tell in a tropical area what is a wetland, what's not a wetland. Because if you take the image on the right, you will not recognize that a lot of the area will be flooded during the rainy season. By the way, this is Samuel in Rondônia, which was, as we all Brazilians know, a major ecological disaster. The dam was built completely wrong. So it inundated much bigger area of forest than what it should have. In any case, without having images from various seasons of the year, you would not be able to reconstruct the actual land cover, because you would think that some of the areas which are in fact flooded are deforested. So this is an example that my friends in Embrapa have produced using a software that is online called SatVag. It's basically take MODIS and DVI time series over the last 25 years. So the response here, if the graph shows in the x-axis years, January 2009, 10, 11, so each bar here is one starting of 1 year, and the value is the value of the NDVI. So high values of the NDVI up to 2003 showed that this area was a forest. Then you have a strong break in the NDVI, indicating the area has been deforested in 2003. Then you have a signal like a sinoid, like a sine, cosine wave, which changes mildly during the year, which is very typical of pasture, which go on from 2004 to 2012. And then you start seeing a completely different sign, which is peaks and troughs, peaks and troughs, peaks and troughs, and sometimes one peak, sometimes two peaks. And this is typical of temporary agriculture. And the two peak scenarios is that you have a safra, safrinha, so you have double cropping. So you can see that for agriculture, there is an argument that you need to use time series as a basis for agricultural statistics, because you can understand well what has happened to your land cover and land use. And so just not to forget, just that we remember things. So we start by the collections available in providers, Microsoft, Amazon, Brazil Data Cube, Copernicus. We build regular data cubes. Okay? From these data cubes, we get signals. Okay? So each pixel gets a signal if the data cube is organized correctly. And finally, out of the signals, you obtain a land cover mask. So the process can be summarized more or less in this way. You obtain harmonized analysis-ready data. You put this on a cloud collection, which is not necessarily you, but Microsoft maybe. You build a data cube, and then comes the really hard part, the part that you cannot give to anyone to do, it's your own. It's the part that you are responsible for selecting training data. Training data is the typical and hard thing to do, because you have to decide what is what, how many classes you want, and you have to decide, you have to know how to run some quality control procedures and to train the data set. And from the point of view of the agriculture and NSOs, you might remember the excellent presentation which was done by Sophie Bontemps yesterday. And she mentioned this top right point here, which is just a box, and then Sophie uncorked the box. Sophie said, remember that data collection for agricultural census is not necessarily today the optimal strategy to be used in the same way as data collection for remote sensing. You need to plan in advance to be able to use your data collection for both purposes. A lot of data collections for agricultural census is done on a non-spatial basis. You ask the guy in front of his farm, how much did you produce last year? And you aggregate that. You know, in aggregate, that works fine, but it would never work fine for spatially explicit work. So that's why the availability, the fact that we may have in situ data available produced by traditional agricultural census does not guarantee per se that that data will be useful as it is for remote sensing. That's why you need to do quality control on that data to make sure you have a daily training data set. And then things start more or less to become quasi-operational. You select the method, you classify data, you smoothen data, you do post-processing. This is something like a workflow that you can put on a script. You know, all of these here, the only part that you cannot necessarily ask a script magically to do for you is really the quality control and the training template. And there are different algorithms. It's not in the purpose of this lecture to give you that. I mean, we're doing an overview of things. Random forest is, I think Lorenzo spilled the beans the other day. He said correctly, look, random forest is a strong baseline. In doubt, start with random forest. It gives you baseline. There's also dynamic time warping. Each of these algorithms will take about half an hour to explain. So this is not, I mean, just to tell you that they exist. And also algorithms like temporal convolution or neural networks. Again, in TEMP CNN, we're entering the domain of deep learning. And you can approach deep learning in two ways. You can say, hey, I'm going to study and know everything to do with deep learning, and I'm going to study the mathematical things, so the mathematical underpinning, so I can use deep learning. That's option one. Option two is I rely on groups that have developed user-friendly software who allow me in an intelligent way to select the best parameters and use these best parameters for my application. We call this like a car. You call this tuning. So you don't need to know necessarily what is inside each of the black boxes. This is something that you have to bear in mind, how supportive is the software that you're going to use for you as a user in order to avoid the complexities that come with deep learning. Well, this is one example. This is classification de Cerrado using TEMP CNN. It is Cerrado biome, 200 million hectares. This is the map of land use, land change for year 2018. It was collected by 48,850 samples. And by the way, the samples were not collected in the field. The samples were collected by the wisdom of the clouds. So the person who did this map, on the occasion, my PhD student, put 3 map sources, IBGE, LAPIG in Goiás, and Global Forest Watch, and so on. And where they coincided, he took the value as valuable. Where they didn't coincide, the labels, he discarded them. So he ended up with, started with 100,000 samples. He ended up with 48,000 samples that IBGE and Goiás and Terra class agreed. So he said, okay, I have a more reliable data set. I'm believing I'm standing on the shoulders of the monsters and geniuses. So it has a 16-day time series. That time we processed 8 terabytes in 24 hours. Now it's probably faster. and it achieved 86% accuracy with 10 land use land cover classes: annual crop, cerradão, cerrado, native non-vegetation, open cerrado, pasture, perennial crop, silviculture, sugarcane, water. This is how it was done in SITS. This is not a course in SITS. We have the occasion. I had the occasion of preparing one for IBGE, and I would be, if the test team wants to set up webinars so we can do it, fantastic. I was very lucky to have been asked by Lorenzo to do a 1-year training, capacity building for Colombia, Chile, and Peru, and must thank very much Lorenzo for the opportunity. I learned a lot. I hope they have learned as well. We went step by step into each of the procedures. Now they're going on their own, but it took some time. But in any way, I'm not here to say this is the best. This is what we know how to do, and that has produced us some interesting results. So the idea is that it takes time series, does clusters analysis, classifies the time series one by one, and then produces classified raster maps. And there's an online book which describes the software. Okay. Now, to explain a little bit how much time do I still have? I'm now running on half an hour, right? Hello? Is there anyone there? Or are you all going mute? Hello?
Gilberto, we have Vivindo Cardoso Medeiros with a raised hand.
Okay. Before that,
Sorry.
How much time do I still have? I just want to know. I've spoken for half an hour, so do I still have 5 minutes, 10 minutes? What?
You have, let me see, until, well, I think you have, there is a demonstration planned for SOM until 11:15, so you have more 30 minutes if you want to use.
Yeah, but I think wasn't the demonstration to be done by Stefania from Chile?
Oh, okay. Then
Lorenzo, is that correct? I had the impression that it was Stefania who would present her work with the SOM and so on. I can do it, of course.
Okay. So Stefania is scheduled to start 11:15.
Okay, so I can. Okay, fair enough. No problem. I can demonstrate and discuss this. No problem at all. But there is a question from Levindo, which we should not forget. Levindo, please.
I think Levindo raised his hand.
Right. Yes, so I'm asking.
It was a mistake.
Oh, it was a mistake?
I think so.
Oi, no, now he has.
Yes, just a mistake.
Ah. Okay. So part of the Brazil is a hard country to do land use classification. And one of the hardest places is the Cerrado. And those who are not Brazilians, well, it's very similar enough to the African savannas that has. The Cerrado has, if you talk in IBGE terms, they actually talk about the Cerrado as having forest formations, savanna formations, and grassland formation. So the Cerrado is more than just a savanna. The Cerrado is a big area which has forest formations such as woodland here. It has some savanna formations such as the picture here, like Cerrado Estrito Sensu, which is areas which the typical Cerrado, with areas and some shrublands together with the areas. And finally, there's open cerrado, which is more grassland formations and shrubland formations. And it's extremely tough to distinguish these categories. In fact, if we consider now one reference map, this reference map is the ESA world cover. The ESA world cover is a reference map done in 10 minutes, 10 meters in 2020. They have another one in 2022, but the same. And well, if you look at them, they have categories here, which are tree cover, shrubland, grassland, cropland, built up, bare, spare vegetation, snow and ice, permanent water bodies, herbaceous, mangroves. Okay. So the idea is that these are land cover categories for the whole Earth. Now, how well do they fit the Cerrado? And what is the context for this question? The context for this question is that for biodiversity and for emissions and for land use policy in Brazil, it is very, just a minute. Outside noise. So it is very important to have a separation between what we call the natural savannas, which are biodiversity rich, although do not have the same glamour as the Amazon forest, and the pasture lands, which have been invaded by cattle, which of course are man-made and have an impact on biodiversity conservation and emissions. Now, as I told you, we did a map which provided the difference between the three types of cerrado and the pasture. And this was done, like I said, this was done in sits, just for you to understand the logic. The logic is you write a script. You say, well, I create a cube or the cerrado, and my area of interest is a shapefile with the cerrado for the year 2018 or 1718. And of course, all the trick is here that you have already 48,000 samples, which you know where the good data lies. So you have the samples, and then you train these samples with a model, in this case, STEM CNN. And then you say, okay, I have trained the model. Now I classify my whole data. So these are 50 tiles, or 50, more than 50. A lot of tiles, I don't. How many? They don't say. It's 200 million hectares worth of Landsat tiles. That's a lot. That's what they see. I think I'd like 100 tiles. Yeah. And then when you say classify, it will classify the 100 tiles. And then you smooth and say, okay, I'm going to smooth. And this is smoothing is to clean out outliers. And then I'm going to label the classification because I have the output of smooth is percentages. Now I create a map. So this is all there is to it. So if you have your data and you know where to get it, you do it 1, 2, 3, 4, 5, 6. This is the whole script that classifies the savanna. You don't need more than that. And then how does it compare to the data that is being published by World Serial or World Cover? Well, it compares quite well. This is the same area. You can see here the same river, and the colors are similar. Where strongest green is we call cerradão, they call tree cover. But the nice thing, and then some areas which they call cropland, for example, these are the areas in rows here, in red rows, and we call them in red, and they are not so different. They are more or less the same. The big difference lies between the whole, what we call the yellow part of the map, where the yellow part of the map is labeled by ESA as grasslands. So if you look at ESA map, the Cerrado is a big grasslands. Now, if you look at our map, it's not the same. The Cerrado is a mix of pasture, which is invasive, exogenous species, human-made. And on the other side of this river, there's a lot of what we call cerrado, or an open cerrado, which is the natural vegetation. So if your reference to decide on biodiversity loss is the ESA world cover, you would be completely fooled by the extent of biodiversity loss in the resident Cerrado, or you would never know how to calculate it. So really, the importance of having not necessarily the best classifier, in which case, yes, we use the better classifier than them, but that was not the point. The most important point is that we had better training data. That was the key difference between the quality of the two maps. And nowadays, this is part of the effort, which is done by BGE, INPE, and Embrapa with the Terra class Cerrado and so on. The latest results that we're working on, we are working on replacing Broadest. Or replacing, it's a tough word, but reducing the effort required by visual interpretation for deforestation mapping. In other words, our aim is to reduce to a minimum the current strong effort done by visual interpreters in defining newly deforested areas. And this is really tough. One thing is to have a map where there has not been one before, or that has been one like done with people who don't know the place, like the Europeans. But this is a map where there are good maps done by good interpreters. And you have to decide which classes you want. For example, we decided something which is not obvious at all, that decided to not to have a class, a land use class called deforestation. We said, well, natural thing is to have one class forest and one class deforestation. And we said, no, this doesn't cut the cake. We need one class which is just the burned area, the areas which are burned. One class which has the cleared area, the areas which are cleared. And one class where there's clearing, but then some vegetation was allowed, or they didn't do it properly, to come back. And we also, so these are all three kinds of classes, and we also went to lengths to include our favorite beast here, which is the seasonality. So here it is the same area, flooded in one season and not flooded in the other. And the other kinds of forests, which are riparian forests, which are also very responsive to water availability. So we then produced a result, which we're very happy, which we agreed at a 95%. So the algorithm agrees at a 95% level with the agreement of the visual interpretation. Okay, so this is why I still have, well, just to finish up. This is a product of a build team, okay, which is working Some of them are EP employees, some of them are Embrapa employees, some of them are corresponding researchers internationally, some of them are hired as soft money. So a lot of people working together. So to finish up, I will discuss a little bit this question of SOM and while anticipating the okay. So like I said, this is for those of you who have never seen, this is the online SITS book, which describes our software. It's online at this address here. I'm going to put it on the chat. Where's the chat? Where's the chat? Chat. Optimize people layout. Chat. Okay, you can send members because you're not members of the chat. Oh, what can I do? Okay, Paulo was kind enough to do it. Okay, Paulo, thank you so much. Okay.
No problem.
So this is the book which describes the SITS, and it's a self-learning book. The idea of the book, it's you learn by reproducing all the examples. It takes time. It's not like you come in and you go and start the first day and you're already doing. It's written step by step, but essentially it's a book where you can copy and paste the code. So there's a code here which you have, and then all the code is copied, and if you copy this code and paste it on your interpreter, you would get the result shown here in the figure. Now, the point I was asked Lorenzo to complete was the key discussions on improving the quality of training samples. These are key discussions, and I'm going to ask you for 2 minutes just to take a cup of coffee, and I'll come back, and a cup of water. Would you bear with me with 2 minutes, please? Okay. Thank you very much for your patience. So what we said is that nothing influences more the quality of your final work as the quality of the training sample. Of course, in general, if you use Sentinel, the results will be better than using Landsat. But if you use better training samples, you can even get the same results with Landsat if you use them. Now, the example I'm going to discuss here is actually available to make it easier for you to remember it and to study it. I'm sorry, please. Excuse me. This is a question. Okay. If not, I've chosen to present to you an example which is available in the book so that you can reproduce this example at your own leisure. Okay? So essentially, we start by a set of points collected from various sources, and sometimes we have a problem, for the Cerrado region. And we have different classes: dense woodland, which is Cerradão, dunes, fallow cotton, which would be pousio algodão, for Portuguese, millet cotton, milheto algodão, pasture, rocky savanna would be the formations, the shrubs associated to savanna, savanna, which is the Cerrado stricto sensu, savanna parkland, which is more the Cerrado, the open Cerrado, silviculture, which is a planted forest, and soy cotton, so soy with cotton, soy with corn, and soy with fallow. Now, the first thing you notice in this data set is the fact that it is imbalanced. Why do we call this imbalanced? Because there are classes which 10,000 samples, which 9,966, which of course cover 20% of the samples belong to a single class. And we have one class called silviculture, where less than 1% of the samples, they belong to this class. And this is a recipe for trouble. When you look at such a data set, you need to become worried. Why? Because most algorithms, most machine learning algorithms, they are trained to maximize the overall result, minimize the overall loss. And then we had an example in Peru, which was a funny example, where 85% of the samples were samples of rice. So I was telling my friends in Peru, I said, okay, that's the easy case. Make a classified map where everything is rice, and your overall accuracy will be 85%, right? So when you have such an imbalance, it's easy to do a map. Just say everything is rice, and you get a very high overall accuracy. Again, you see overall accuracy not... Hello? So you need to approach these beasts step by step. The first step is to do a cross-fold validation. How many of you are not familiar? Please show a show of hands. Or
Gilberto, I
Gilberto,
think your microphone is
Sorry,
disconnected.
Gilberto.
We cannot
hear
hear
you.
We cannot hear you.
are you hearing me?
Now
Yeah,
we
right
can
now.
hear you.
Now, yes.
Yes or no?
Yes,
Yes,
I
now.
can hear you.
Okay. For some reason, my microphone got away. Okay, now you can hear me.
Yes.
Okay, let
Sure.
me. That's it. Because I'm in a building. They're doing lots of. Second, please. Is this stupid stuff? Oh, just a second. Okay. Master output level, input gain. Okay, so now we are copy of broadcaster. I hope that you now hear me better. Even better now, right? Oops. Okay.
Yes,
Perfect.
it's perfect. Thank you.
Okay,
We
good.
can hear you very clear.
All right. Absolutely. Thank you so much. Sorry for this. Okay, what I was saying is that I'm supposing, I don't know if you hear what I said. I asked you, how many of you are not familiar with the concept of cross validation? And no one raised a hand, which means that you are all familiar with the concept of cross validation, which is very good. Someone raised their hand. Okay. So
We have a few questions on the chat, Gilberto. I'm not sure if you want to address them now or at the
yes,
end.
I should address them now.
Okay.
Where's the chat? Okay, I can hear. How is the feature space? Okay, very good. Okay, let's start with this. How is the feature space using the cube methodology? Are they also defined as a cube bed and don't need feature space? Some reducer from NSDCI minimum. Okay, good question. So, are you seeing me? Okay.
Yes.
So let me try to both share and see the chat. And I'm not sure I can share and see the chat. Can I? No, this is strange. No. Okay. So feature space. Think of the following. Let's go back to a very good point by Eliana. Okay, I hope this helps. Okay, imagine that, Liana, imagine that you have a single image, okay? Single Landsat image. And you have five points, five bins, okay? And if you have a traditional classifier, in this sense, we can say that the feature space of a 5-band Landsat image is 5-dimensional. And we can also say that the algorithms like random forest or support vector machine or maximum likelihood deal with this feature space in the same way they would deal with the census feature space. So, you know, if you put up a census and do some regression on the census, number of children per household or whatever, income per household, all these variables are taken as is, right? And normally we don't explore any spatial relationship between them. Okay? Yes or no? Please, someone. Hello, Eliana, can you answer?
Yes.
Yes.
Yeah,
Okay, so just a question. When you ask me and I ask, okay, I need you to please come back to me and say yes or no, so I don't know where I should proceed or not. Okay? Now, let's continue here. Imagine now that instead of 5 bands, you have now 5 bands and 12 months of data. So you now have a time series of, the time series does not have 5 values. A pixel has 5 values. A time series, there are 5 time series of 12 values. So here we're talking about a 60, a dimensional space of dimension 60, right? Yes or no?
My question, it was about if we can introduce this NDSI mind reducer in the construction or in the realization of the cube data.
Right.
Is it that possible?
No, it's possible, but it's not
Okay.
recommendable. My point here is you can do a reduce. I mean, the code, the software allows you to do a reduce, but why would you do a reduce? The point of reducing, this is a very important point. You can always take 12 images and make one. This is what Google Earth Engine does. It's called the geomedian. And my question to everyone is, why would you do it when you have 12? 12 by my last count is bigger than 1. So why should you reduce?
I need to detect or reduce the noise in the cover, right? For example, in snow. If I want to detect the glacier, yeah, I need to reduce the noise that is produced by the snow, the temporary snow. So I need to detect these, I don't say like comportamientos, and that are I don't that are like I don't know who say that. I mean, like maybe the temporary snow, the snow that is temporary, affect my classification. So
Okay,
that is
fair
why
enough.
I use a reducer, for example.
Okay, but my point here is you can be more clever than that. Yes, there will be points on this time series which will have noise. Okay? Now imagine a Sentinel time series with 16 days, 23 images per year. Out of these 23, let's imagine that there are 10 points with noise. Okay? So so imagine a time series like this here, and imagine that every third point has got noise.
Mm-hmm.
But the other points have information, right?
Right.
Some points have noise, some points have information. So what do? You do what you do with time series, you interpolate. So you use the points where you have information to infer the value of the points which are noisy. So your algorithms will always use valid points because you always interpolate between noisy points.
Okay. Is there an interpolation in the cube? That's the point?
Yeah, no. There's an interpolation in the cube, not in the cube, but in the algorithms which use the cube.
Okay.
Okay, so let me be more specific. I think your question. Okay. So when I do something like this, okay. Okay. So this is SITS, but it could be other. Okay, SITS classify raster groups. Okay, what are the parameters that it takes? What can you set up? Okay, the cube, the model, your region of interest, an exclusion mask, a smoothing filter if you want to smooth, and this is why you're asking, an imputation function to remove NA. So you can put here an imputation function, linear, smooth, whatever curve you want, and removes the NA, starting date for classification, and then you can set up memory available GPU, batch size, and so on. So the design of the system is so that it takes in account the fact that you have good data and noisy data, and uses the good data to infer information on the noisy data. What we don't want is people, when we designed the system, the last thing we wanted is to have a clone of Google Earth Engine. To have a clone of Google Earth Engine and use Google Earth Engine. So our argument is, what is that everybody uses in Google Earth Engine that can be improved? And it's the GeoMedium product. I said, no, let's not use the GeoMedium product. Let's use a proper time series so you interpolate. Now, it's 11:19. What I'm going to do, I'm going to take one more question and then pass on to Stefania, because what I was going to show, Stefania will also show in a better way than me. So let's take 5 minutes for one more question. Otherwise, you don't have time to interact.
All right. Thanks, Roberto. That's exactly what I was going to ask. So we have one extra question, which is from Coronado Irregas Albel Alejandro, asking, what is your opinion on segmentation as an alternative to pixel-based classification in crop mapping?
I can send you the results we had. Send me an email, send the results we did in Peru. I mean, there are two segmentations now. There is the segmentation, which is the traditional segmentation, where you break the images in segments by algorithms like supercells or something of this order, which is available, for example, in Google Earth Engine. You segments. And then you classify the segments, and it's about the same thing, not providing any magical, but I'm assuming, and please confirm, that you're talking about semantical segmentation in the way that the UNet does. Is this what you're talking about, Coronado? Puedes hablar en español si quieres, ¿eh?
Gracias. No, estaba hablando más bien de la clasificación tradicional, pero me parece muy buena idea lo de la segmentación basada en deep learning que mencionó.
Sí.
¿Podría elaborar sobre eso?
Sí, claro. Entonces, so the idea of deep learning, these techniques, is that they are based on the tradition of computer vision and the tradition of photo interpretation, like your iPhone or your Android, which is to distinguish background from foreground. And the idea is that they take RGB patches, so like 256, and then they segment features in the landscape. And these features in the landscape might be buildings, for example. It's being very much used. There's an algorithm method by Meta called segment anything, which works well for very high resolution images. For middle resolution, 5 meters, 10 meters, 20 meters, there is the distinction between foreground and background, like a face of a person and the background that is before, has no meaning. Everything is foreground, everything is background in a remote sensing 10-meter image. So the jury is out. There is a groups working on it. The jury is out that I have not yet seen a really powerful application wall-to-wall of using semantic segmentation to do classification. What I have seen is the use of semantic segmentation to define field boundaries. That is what Ian Nunes from IBGE is doing, which is very interesting. But he doesn't, at least the papers I know, Ian is probably here, so he could tell us. He uses this as a field boundary delineation, and then you still need to do the data collection and the classification for each field. And I think that's it.
Thanks a lot, Gilberto.
Yeah.
So let's give the floor to Stefania, right? Otherwise, I'm stealing the floor.
Right. Thanks a lot. Stefania, the floor is yours. Thanks a lot for your participation.
Thank you. Well, I share my screen. You can see my screen?
Yes, we can see it. Thanks a lot.
Thank you. Okay. Well, as mentioned by Gilberto, I'm going to present our work. We have working about a year with Gilberto and his team. And we are it's a pleasure for me to present this work and what we have done in Chile and the development of this case of study. It's about improving the quality of training samples in the construction of land use and land cover maps. In a special case study in a Maule region here in Chile. Well, the contents of this presentation are divided in 4 sections. The first one refers to the context and motivation of the development of this work. Then we are talk about the workflow. For the focus of this presentation is our case of study, with particular emphasis in the point 3.4, improving the quality of training data. And finally, I will share some reflections on the key lessons learned and opportunities from improvement that we identified by the technical team that carry out this pilot project. What is our motivation for the development of this work? Well, currently, there's not land use and land cover maps in Chile focused on the production of agricultural statistics. This, coupled with the institutional need for an accurate and up-to-date sampling frame, creates the needs for this tool. We see as an effective solution to mitigate this was the incorporation of remote sensing and its combination with machine learning techniques. A pilot of land use and land cover map was developed in a region of Chile. This pilot map covers the 2020-2021 agricultural season that covers the last agricultural and forestry census developing in Chile. In this part, I briefly remember that talked previously by Gilberto about the workflow of this work. This diagram summarizes all the steps that we follow for our work. And first, our first step was the request of our ERD image collections for build and regularize a data cube. Then, based on ground data, we extract time series and we obtain the samples, time series samples of the ground data. In this part is the most important part of the work, where we analyze the quality of our training samples. Once we finish this part, we train a model using machine learning algorithms to finally classify and generate a classification map. This classification map is not a final map that we use. We applied a spatial smoothing utilizing Bayesian smoothing, and then we obtain a final classification. And for the validation of this map, we utilize the group practices, including sampling design, reference data collection, and accuracy and area estimates, based on the good practices recommended by all of us. This is the workflow we use for our pilot project. Now, the core of the work is our case study. This was in Maule region. This region is located in central Chile, and it covers approximately the 4% of the surface area of the continental Chile. It represents almost 17% of the national cropland according to the last agricultural and forestry census. Its topography presents coastal plains, as we can see in this part of the map, central valleys, and mountain range. Yeah. According to this picture, in the central valleys are located the croplands. It's a very important surface of croplands in Chile. That is, for this reason, is a region of very interesting for develop this pilot project. Now, regarding the satellite data, we use a regular data cube that we build using seeds package in R. We follow the seeds methodology supported by seeds package in R. We regularize data cube based on information from Sentinel-2 satellite with all optical bands plus 3 spectral indices. It covers 1 year, 2020, 2021 agricultural year. Also, considering the topographic variations in the region, we incorporate the incorporation of them was fundamental to better characterize the territory. As you can see in this illustration, this information is added as one more band to data cube and is considered as a multi-temporal layer. Our training dataset was built using 2 data sources. One of them was the information of the 2020-2021 agricultural census, and the other source was national cadastres. However, both have limitations. In the case of agricultural census, this source was not designed to produce land use and land cover maps. The ground position data is approximate rather than precise, and we use filtering methodology operates under single crop assumptions. We try to rescue this data and give a special context. About national cadastres, these were not intended also for land use and land cover generation, and these products lack standardized classification scheme. So we should work with this information, and for this we use a methodology that consists in 3 steps. First one, it's a using on and DBI time series analysis for phenological stage tracking. 2, seasonal RGB band combinations to detect temporal spectral variations. And number 3, expert-led interpretation of BHR imagery from the period study. After this procedure and revision of this information that we have, the polygons of the training was generated. This is why improving the quality of training data is of greater importance to us, considering the use of non-standardized sources. Additionally, it allows to us assess whether a correct classification scheme was generated. Finally, the sample has a little over 34,000 data in number of samples. With a scheme of 3 levels. Okay, at level 1 there are 8 classes. At level 2, 11 classes, and at level 3 we have 23 classes. Our modeling was carried out at level 3. As you can see in this table, the imbalance that we have in our sample train, where planted forests account for 16% of the total of the sample, And for the other side, vegetable crops have represent only 1.3% of the entire sample. This imbalance is a key aspect to consider in the approach used for analyzing training data quality. Now, improving the training of data quality. As mentioned before, the data sources were not explicitly designed for the construction of land use and land cover maps. It is essential, for this reason, analyze the quality of the training samples before applying them to a classification model. High-quality training samples are needed for the design of remote perception and the success of the machine learning techniques. We use two methods that are present in SIDS package for this item, for improving the quality of training data. One of them is a self-organizing maps, SOM, and the other is a synthetic minority oversample technique. In the case of SOM method, we can divide in 4 steps. The first step consists in have or a satellite image time series data obtained from a regularized data cube. The second step is apply a reduction of dimensionality based on self-organizing maps, where SOM compresses this high-dimensional data into a 2D grid, preserving topological patterns, as we can see in this part. Then it would use a Bayesian inference to change its probability to belong for one or another cluster. Neighborhood relationships in the SOM grid are analyzing by using Bayesian method. Initial cross probabilities are updated to posterior probabilities by incorporating spatial context, adjusting class assignments for consistency. And finally, once we have these two probabilities, we apply noisy filters based on thresholds. Yeah. Okay, samples are evaluating against thresholds for conditional and posterior probability, as we can see in this schema. And based on some conditions, we can identify outliers or noisy samples. And these are flagged to remove or keep in our data set. This is the principal functioning of this method. In the other side, SMOD reduce class imbalance as we have in our data set. What we do SMOD is generate synthetic data by interpolation of the neighborhood, more than duplicating data. Okay. Important is to comment that in the case of SIDS package, their undersampling of using in this part is using the SOM method, where the undersampling is made by this method. Now, to evaluate the quality of data set, we applied 4 tests to choose what is the best training data set. The first test is our baseline, our original data set, where without cleaning noisy samples with some filtering or applying smooth, we have samples noises, and imbalance. As a diagnosis, we can show this sum up as the first result of the analysis. This is a clusterization of the samples. And we can see there's clear groupings, but another neurons are in wrong places, such this. This may indicate that probably is a mislabeling sample or with a high noise in his information. In this part, we can see a very good grouping between forest plantation, and at level 1, the wooded areas are well identified, as we can see also in the part of perennial fruit trees, and also in cereal, late season cereal. Also, the water bodies are well clustered in this area, and snow bodies and snow and glaciers are very well grouping too. The next step in the zone-based quality assessment involves analyzing label confusion. In an ideal scenario, all samples within a cluster would belong to a single class, reflecting a clear and accurate classification. However, in practice, cluster often contains samples with different labels indicating classification confusion. This information is a key to identify and quantify class overlap and therefore to evaluating the quality of the training dataset. Label confusion can be visualized using a bar chart like this picture that represents initial mix of classes in the training sample. In general, some classes are well differentiated with a single color dominating each cluster. This is the case of water bodies and snow and glaciers, and we have a very low mixture with other classes. However, other classes show more confusion with similar categories, suggesting spectral or contextual similarities. For example, agricultural classes such as early season cereal and late season cereal partially overlap with vegetables and forage, likely due to similar spectral patterns in the optical or indices we use. Likewise, forest classes such as planted forest and young planted forest show confusion with deciduous native forest. There's some confusion between wooded areas. There's also a significant overlap among bare soil classes, such as rocky soil and sandy soil. This class presents only a 50% of purity of his class. Cross-validation, which should be understood as an evaluation of the internal consistency of the data, shows an accuracy of this dataset of 0.92%. And FAU scores range between 0.6 and 0.99. Sorry. And well, in this figure, we can see the noise of the samples. According to the conditional probability, each sample can be identified as clean, removed, or analyzed. This helps to give an idea how much the samples belong to a particular class. Within the high confidence classes, sandy soil, artificial surfaces, and harvested forest plantation stands out with at least 18% of their samples classified as clean. On the contrary, some classes show high uncertainty, such as perennial fruit trees, vegetable crops, young forest plantation, shrublands, mountain shrublands, grassland, mountain grassland, and lands above altitudinal limit, where a large number of samples were labeled as removed. This suggests a possible class overlap or inconsistencies in labeling. Okay, we can see the 76% of the samples should be removed, and only 24% as evaluated as analyzed. These classes didn't show samples identified as clean. So this is a sign of something happened with this class, and we have to put attention on this. The second test involves cleaning these noisy samples. Once we make the evaluation, we applied a filter, eliminating the noisy samples using the filter sum. And we have this bar chart that presents the new confusion between classes. And now we have around 26,000 samples. The range of proportion range between 1.2 and 50%. The imbalance maintains it maintains in the samples. But according to the previous picture, some classes experience a significant reduction in the number of samples, as we mentioned in the case of mountain shrubland. Despite this, we can see, for example, like season cereal, where didn't have confusion with any class, it's 100% purity. Also, the metrics show an improvement. The accuracy is 0.96. If one score range between 0.62 and 1. This graph reflects a data set with greater discriminatory power between land cover classes. This is an improvement in the separation between classes. Now, we want to try another method to deal with the imbalancing of sampling. For this reason, we applied smooth or data set. In this case, the number of samples is just over 25,000. But in this case, the proportion of the class range between 3.6 and 6%. Is more small, while the total number of the sample is similar to previous tests. This dataset offers a more balanced class distribution. All cross-validation metrics show improvement, but to a lesser degree than in test 2. A reduction in class confusion is observed with a lesser extent than with the sum filter. The bars are smaller. Only snow and glaciers are near 100% of purity. High confusion persists in forage and improvement in grasslands, as well between shrublands and mountain grassland. Finally, we try a method with an assembly of process, where first step was cleaning noisy samples using some method, and then deal the imbalance with smoke. In this case, we can see around 18,000 samples with proportions ranging from 1.3 to 16%. In this figure, we see a marked separation between classes, with confusion percentages between classes are not exceeding 5%, in the case of shrublands, in this case here. The forage class continues to show confusion with improved grassland, as does early cereals. But in this case, is a more purity data set. The classes are very well differentiated, and his metrics shows a very high improvement on accuracy 0.99, and the FAO score range between 0.96 and 1. Okay. For each these 4 tests, a random forest model was trained. Each model was then used to classify maps, which are shown in this picture. This step is very particularly important for determining which model will be selected for our final validation. In the upper left corner, a high-resolution image is shown of an area of Maule region. And according to 2019 land use map from CONAF, this area is characterized by a high prevalence of forest plantation, native forest, and shrubland, how we can see in this picture. The other 4 images represent the classification maps produced by 4 datasets and the trained models. All this classification differs in the predictions, are not the same, but test 4 stands out. Why? Because it's showing a substantial amount of agricultural land in an area that there's no agricultural land. Yeah, this contrasts with the actual land use observed in the reference data. Now, how we select the best or the most according map to the situation? We choose the test 3 for 3 reasons. The first one is we have a balanced training data where we applied 2 statistical methods, with one mode mass some guided undersampling. The second is a correct identification of native and forest plantations, and we have a high consistencies in the ground data. Yeah? We respect the agricultural patterns and not overestimate cropland areas in other areas. The other tests were rejected. One, we have class bias on unbalanced samples. Test 2 shows high accuracy, but exacerbating balance. And test 4 overestimate crops in forested area, as we can see in this map, where we have fruit trees in areas where naturally is forest plantation or native forest. So we finally choose the test 3 for make the final map and make the final validations. Once the model to be used is selected, the prediction is performed from entire region. Yeah, then Bayesian smoothing is applied to reduce salt and pepper effect. Finally, validation and accuracy assessment was carried out following the good practices recommended by Olofsson and supported by FAO. While this is not the focus of the presentation, it's important to mention that sampling design, sample labeling, and the estimation of both accuracy and area were properly conducted. When he can see briefly the agricultural lands and its accuracies for users and producers. This is for level 2, and this is for level 1, with a very good accuracy, and overall adjusted accuracy at level 1 of 0.8. Okay, finally, this is the final map generated for Maule region at level 1. Despite some class confusion, the map is consistent in showing agricultural land concentrated in the Central Valley, while higher elevation areas are dominated by tree vegetation, non-vegetated soils, and snow. Finally, our conclusions and recommendations and what we have learned in all this process. A high quality land use land cover map should reflect spatial reality, not just optimize accuracy metrics. Over-reliance on clean samples can lead to overestimation and reduce sensitivity to complex patterns. Combining satellite data with expert knowledge and ground truth ensures ecological and contextual relevance. Align classes with spectral and phenological traits reduce class confusion and improves interpretability. And finally, use hierarchical system, functional criteria, and dynamic sampling to better represent landscape diversity. Well, this was my presentation. Thank you so much, everyone.
Okay, so we have a few more minutes for questions. I see that Gilberto has a raised hand, so let me pass the floor to Gilberto. No? Okay. In this case, I have one question to Stefania. Stefania, in the case of the INE Chile, how was the collaboration with FAO structured to implement those methodologies? And what lessons would you share with the other NSOs trying to do the same?
The most important collaboration was this part of analyzing the quality of the data. In our case, we build our data for training. We don't have any in situ data. So more than the process or workflow from seeds, that was very important to us. The core of our learnings was apply this method. How to identify mislabeled samples, or maybe if we have a problem with our classification scheme, if we have to make some change. In our case, this leads to change our scheme. We have now a new scheme focused on phenology more than agronomical. More than agronomic, is more phenological development, and this was fundamental to identify how our samples are grouping, and we have a very scheme. I think this was fundamental.
Thank you very much, Stefania.
Thank you.
Well, I think we don't have any other questions then. And before we close, I would like to extend our really heartfelt thank you to our presenters today, both Gilberto and Stefania, and to all of you that shared moments with us during this week. To our presenters, we deeply appreciate the flexibility, the professionalism, and the patience through the workshop and the dedication of your time. It was really essential for the success of this workshop. Okay, so in final comments, as I mentioned in the beginning of our session today, all participants registered will receive an email, okay, with a link for our Moodle environment, and we'll be able to download the certificate from this week with us. Thanks a lot, everyone, for your time, and I wish you, all the participants, a very good weekend. Okay, thanks a lot. Bye.
Thank you.
Thanks a lot, Paulo. Bye.
Thank you. Bye.
Bye.
Bye-bye.
Thank you.
Thank you.
Bye-bye.
Bye. Thank you.
Thank you. Bye-bye.